Good morning, everyone. How's everyone doing? Anyone have any questions before we get started? We got a few minutes
I
left.
do. I have a couple.
Go for it, bud.
Okay, so it's hold on. It says on my canvas here that I still have yet to do test 2, chapters 3 and 4, which I already did, by the way, though. It says that I have accommodation test 2 and test 2, chapters 3 and 4.
Let me check that at the end of class. I'll see what's going on with that.
Okay, and also, we're not supposed to do the constellation tests, right?
You don't have to. No, no. If you want to, you can. It won't bother me, but you don't have to.
Okay. Well, when I didn't do it yesterday, it said, and when I didn't do it on Tuesday, it said that it was missing. Is there a way for you to say that we're exempt from it on the canvas? Because like it's just my paranoia.
Yeah, I'll see what I can. I'll see what I can find out. The odd part is I don't even know where it is, so I don't know. I got to find that first. But yeah, I'll see if I can track that down and turn that off.
Okay, thank you, sir.
No problem.
Um,
Really, guys, remember all you technically have to do every week is whatever chapter we're covering. You want to make sure you read that. Whatever lectures I give, you want to attend those, and then you want to make sure you do your homework for that chapter. So every chapter gets a homework assignment. And then occasionally I will put up practice tests. You should take them many times before you actually take the real test. And then, of course, you take the real test. Everything else is optional. It's for you to earn astro points and that sort of thing. So uh, that should hopefully put your a little bit of your paranoia at rest if you're like me and Matthew, and it just bothers us to see something that we're missing. So don't worry about that. If you've done all these things and you can look in the grade book and say there's a test two, and you've got a grade by it, then you're golden. Okay.
Professor Younger.
So it does sometimes things like it says that you didn't take 3 attempts. Well, if you were happy after 1 attempt or 2 attempts, that's fine too. Go for it, Tyler. What's up, bud?
Remember, before the moon, remember for the moon project, just
Mm-hmm.
a reminder, there's going to be clouds covering up the moon, which is going to mess up our project. And that sucks.
Yeah, but minor clouds covering every now and then. That's not a big deal. Today's really a good day. Yesterday was a good day. So
It
just let's
was
let's look on the full side of the glass. How about that? And remember, I pushed that deadline back way back, so you got
to the
plenty of time, man.
28th next month.
Yep, yep.
Yeah,
You
I
literally can
actually
get
have
it.
good news about that too. Yesterday, I got my first moon, finally.
All right.
It was a
It was up during the day,
yeah, it was
and it was
waxing gibbous.
gibbous. Yes.
You just
Was
have, Matthew, you just have to put like gibbous, crescent, or full moon, or even a quarter.
Yeah. Yeah. You don't
but don't we have to put
actually
like the
have to
height and the
figure out.
direction?
Yeah. Yeah. You need to put the direction you're looking in, the height, which is literally high or low, would be sufficient. The
Oh,
more you
really?
do, the more it's worth. Yeah. You say
So we
high.
don't really have to calculate like the exact height.
No. But if you actually use an inclinometer and do that, that's probably worthy of more points.
How much do you think is that worth?
Not a huge amount. Like
No, no, no. I meant how much do you think it costs? The inclinometer.
oh, there's one built on your phone, probably.
Really?
Yeah.
All
If
right.
you go where the compass is, often the compass has an inclinometer as well. So if you tilt it, it'll and align it towards pointing at the moon, it'll actually tell you what your inclination is.
Yeah, I
At
was
least the
actually
iPhone does that.
so excited yesterday. I got like pictures on my phone. Like I'm considering hanging that stuff up right now because like I was scared for like the longest time that I wouldn't be able to get one of these moons.
Yeah. Well, I saw a funny meme yesterday, and this is related to the moon that project that you're doing. Actually, it was a sexist, typical sexist meme, but basically says they asked the man what kind of wife does he want, And he said, I want one like the moon. And they were thinking, oh, well, that's kind of pretty. I wonder what he means by that. He said, I want one that comes out comes at nighttime and then leaves in the morning. I was like, that's kind of crappy, but also it just completely misses the point. The moon is up during the day too. So, anyways, that sexist meme was what I turned into a teaching moment. So remember, the moon is out during the day. In fact, most of the time. So you can always find I shouldn't say always. There are many, many, many days per lunar cycle that you can find the moon up during daylight hours. Okay. And there's no dark side of the moon. Pink Floyd was wrong. I mean, there is at any instant a dark side, but that dark side changes from day to day to day. Okay. All right. Any more questions before we move on? All right. So we're doing the formation of the solar system. So I'm going to give you what's called the Nebular Hypothesis, also called the condensation theory. But basically, what we believe created our solar system, which the generic term would be a star system. And in our case, our star is called Solus, so they call it a solar system. And in order to do that, you sort of have to have some idea of what objects what objects and behaviors are in the solar system that you want to explain, and what ones exist that maybe you don't need to explain because they're anomalous or something along those lines. So that's where we're going to start off. I made a special PowerPoint for this one so I can put it on the web without worrying about copyright stuff, hopefully. So anyways, let me find it real quick. I'll pull it open for you guys. And there it is. And what I'm going to do is when it opens up, I'm going to do share screen, and it's called Formation of Our Solar System. If y'all look in this week's module, you should see Formation of Our Solar System PowerPoint. So if you want to go along with that, you can, or if you want to do print to PDF and then open it with a Word document so you can type results on it, or even print them out so that you can see results, and that'll be fine as well. I know a lot of people like to use PowerPoints for notes that way, and it actually is pretty good way. I hate the idea of using so much paper, but other than that, it's good. So let's go to my PowerPoint. Okay, so we're looking at the PowerPoint now. I'm going to shrink this down, get it out my way, and I'm going to make it full screen by doing this. Okay. Formation of the solar system, temperature and location, location, location. So that's me using that typical real estate jargon that people say, what's the most important thing in real estate? And they say location, location, location. And that is actually there's some truth to that when we're talking about the nebular hypothesis and condensation theory. I'll point that out as we go along. So first off, we have to do a bit of a survey of the star system that we're in, the solar system, before we can try to postulate a hypothesis about how it came to be. And this is a pretty good, obviously out of scale rendition of our solar system. In fact, when I made a scale model of the solar system, as you guys will do in a lab later, you make a scale model of the solar system. I chose one in which it was a 16-foot diameter sun because I did the calculation and found out that if the sun were 16 feet in diameter, then Pluto would be about the size of a BB or a little smaller than a BB. So at least everybody could see Pluto as a real object or whatever. When you do that scale, though, 16 feet in diameter, that also takes a typical room. You know, most rooms in houses are 8 feet high. So you could literally fit in the corner of the wall, you could fit a quarter of the moon, or excuse me, a quarter of the sun in the wall there. So you can get an idea of roughly how big it is. And then on that scale, we walk out and down a block in Elizabeth City or some other place where I put it, wherever I go to do these demos for schools. We'll walk down the road as a group and see that once we get about 1,500 yards away from where the sun was, we run into Mercury. So the sun, like 16 feet in diameter, is 1,500 feet away from the actual planet Mercury, which is the closest. And then Venus is almost twice as far. It's like 0.73 instead of 0.4. The other one was 0.4. And then Earth, we get on the order of like 3/4 of a mile. By the time you get to Mars, it's literally over a mile. And when you get to Neptune and Pluto, we're talking 30 miles. Okay, so the scale model of the solar system is a difficult thing to do, because if you make it small enough that the orbits fit on a normal piece of paper or even a poster board, then the planets are going to be so small that you can't make a pencil point small enough to represent their size. So it's really problematic to make a scale model of the solar system. The best you can do is sort of like they did on the Mall in Washington, D.C. And that was put together partly by Jeffrey Bennett. I met him. He was an author of the textbook we used to use, or I used to use anyways. But he got a proposal done through Washington, D.C., and I think it was National Science Foundation. And they put basically a sun at one end of the mall, and that's actually right by the Air and Space Museum. So if you walk out onto the mall from the Air and Space Museum, you'll see a sun plaque where the sun's about the size of a grapefruit or a palm of your hand, something like that. And that's the scale they're using. It's a 1/10 billionth scale. And then you walk along the mall, and every now and then you'll run into another little piling, and it'll have a drawing, a scale drawing and description of Mercury, and then keep on going, it's Venus. And then basically by the end of the mall, you're just all of a sudden forgotten about everything, and boom, there goes a piling with Pluto on it. I think it ends up being about a third of a mile away, something like that. So those are practical scale models of the solar system. People have also done them with vehicles in open desert areas, and or at least I think I saw that on a movie. So it might have been something that someone pretended they did on reality. But anyways, the scale model of the solar system is a cool idea, and it really gives you appreciation for how empty space is, because our solar system is fairly densely packed compared to, you know, what we call the vacuum of space. So the odds of something hitting us means is very low because of this not packedness, or this low density area. So if we do go to, say, look at our solar system, I want to take and consider looking up, flying up above the Earth's surface, and then looking back down, and then I'm going to consider moving down here and looking to the side. So let's explain what you'd see when you do that. So if you take off from the North Pole of the Earth and shoot straight upward, say, and you keep flying out and out and out, and you got infinite technology, so you can use telescopes, microscopes, anything you want. You can you have it all there, but you fly up high enough where you can see all the orbits of the planets, and maybe you've got a device that actually can detect where Pluto's been and where Neptune's been and Saturn and all that, and it actually shows little lines for you so you can get an idea of it. And you look back down from above the North Pole, and you'll notice something that's very shocking. One, you'll notice that the sun is rotating in a counterclockwise direction. It's also doing so differentially, which is kind of weird. It's not like a solid object, so like the equator rotates faster than the poles do, like this. So that's kind of neat, but it does rotate counterclockwise. And then you'll notice that every planet revolves around the sun counterclockwise as well. So that's some information we might want to use to help us understand how the solar system formed. Then, with few exceptions, if you look closer at each of the individual planets, you'll see that with a few exceptions, all the planets rotate counterclockwise as well. So that's kind of weird. You'd also notice that the four inner planets, what we call the terrestrial planets, are Earth-like, which is Terras, right? So Terras are terrestrial, means Earth-like, and those four objects are really small compared to the other ones. They're rocky. They have densities around 6-7 grams per cubic centimeter, stuff like that. They're fairly close together. They're fairly close to the sun. They have very few moons. Most of them are cratered, and in fact, one of them's got a really big moon, namely Earth has a large moon, and that moon is quite cratered. And again, they are all essentially, with a few exceptions, rotating in the same direction, but they're really, really small and close together. Now, if you look beyond Mars, you'll see a bunch of orbiting debris that are mostly rocky, and we call them asteroids with an R in it, so that can help you remember the rocky part. And those things obviously aren't just sitting in space, because if they were, gravity would pull them right towards the sun. No, these things are actually in orbit, mostly in that same counterclockwise orbit. Okay, so they're revolving around the sun in a counterclockwise direction. Then you get a little bit past that, and there's Jupiter, the largest of the planets. And in fact, Jupiter is either 16 or 19 Earth diameters in size, I think it's 16. You can just do the diameter of Jupiter divided by the diameter of Earth, and you'll get the number that I'm talking to. So that's that I'm talking about. That's why I say 16 or 19 times larger. But the neat thing about Jupiter is, yes, it's the largest planet, but it's freaking huge, and it's a lot farther away from the other planets. In fact, we get to about 1.5 astronomical units is where Mars's orbit is, and then Jupiter's is out like 5. Okay, like 5 astronomical units. So, and you'll see later that the other planets are far apart too. So they're really spaced further apart. They all have rings. Every one of them, not just Saturn. Jupiter has rings, Saturn has rings, Uranus has rings, Neptune has rings. Pluto actually has moons, but is no longer considered a planet, and it don't really fit in with those 4 what we call Jovian planets, are gas giants. That's another name for them. And they are made mostly of material that would be considered a gas, or would be in a gaseous state if it was on the surface of the Earth. And most of it's sort of a gaseous state on those planets, but they actually reach some really weird states of matter as well, like metallic hydrogen and stuff like that. So it's kind of a hodgepodge of stuff. They all have many, many moons. I think last year I heard was the latest survey of Jupiter, and Jupiter had like 97 moons. I think it was just under 100, and Saturn had like 80 some. So they have a lot of moons. They all have rings. And they get, actually, Saturn's a little bit smaller than Jupiter. Jupiter turns out to be sort of our apex of size, because when you get as big as Jupiter, if you add more mass, the gravity is so strong that it can actually make it smaller. So it's actually in that state already where it already started getting smaller because it had so much mass. Saturn is smaller than that and not experiencing that effect yet. And then if you look at like Uranus and Neptune, they're on the order of 6, or I should say 8 and 6 times the diameter of the Earth. Beyond that, there is a sort of flattened donut shape called the Kuiper Belt, and those things too are basically revolving in a counterclockwise direction as seen from above the North Pole. And that's actually where Pluto is, and in fact, that's why Pluto actually lost its standing as a planet. Specifically speaking, they decided they were finding all these new exoplanets and also new things around our own star, and they figured they better come up with a formal definition of what a planet is, so everybody, when they say planet in the scientific community, will know exactly what criteria it meets. So the criteria came out to be: 1, it has to orbit a star. Obviously, Pluto does that. Obviously, all these planets do that. Obviously, none of those moons do that because they're orbiting a planet, right? 2, they have to be massive enough to basically be spherical. So what that means is once you get to a certain mass, basically the planet would be in a liquid state, or a molten state, if you will. And because of that, gravity, the gravity of the very planet, which is a central force, is a force that pulls equally in all directions. That's going to force the most dense things to fall to the center and the least dense things to percolate to the top, and it'll be mostly spherical. Of course, if it's spinning fast enough, it'll get sort of flattened and fat around the equator like me. And that's actually what our planet has done too. It's an oblate spheroid is the definition of the shape of our Earth. So that also happens to be a criteria that Pluto meets. So Pluto's still a planet for those 2. The third one is the one that kicked Pluto out, and that is that the planets must be massive enough to have cleared their own orbit. And remember, I told you Pluto's right in sort of the Kuiper Belt, and there's a bunch of debris in there. And we expect if you actually stayed on Pluto for 2 or 3 revolutions, which God forbids a long time, you would be bombarded repeatedly from things in its orbit because it just isn't massive enough to pull things out of the way. What it does is it slowly goes around and it'll tug on something that's fairly near, and then that thing will start moving, and then when it comes back around again, maybe it'll run into that thing next time around. But there's basically a lot of matter and debris within Pluto's orbit, which, by the way, does actually cross Neptune's orbit. So Neptune's orbit and Pluto's orbits actually cross each other, but they're asynchronous. So you're never going to see Pluto and Neptune at the same spot so that they could hit each other. They're actually always at the opposite end, so that works out just fine. Something else you might notice, and we sort of have a origin for this already, so you don't really have to make an origin for it in our solar system. But Jan Oort predicted basically by the fact that we know early on planets were orbiting this way and this way, planetesimals and rocks and stuff were orbiting all sorts of different directions. And because we have these massive bodies like Jupiter and Saturn, and even the smaller ones, when big rocks or whatever, or small rocks or planetesimals come flying in, gravity from these various planets is going to sling them in random directions. So Jan Oort predicted the existence of something called the Oort Cloud, OORT. The Oort Cloud would be a spherical distribution of orbiting bodies. And some will be like comets, some will be like asteroids. And comet it starts with a C, and we think of them as mostly icy. And of course, icy has a C in it, so that helps you with that as well. But be advised, when we finally did take samples off of asteroids, we found a lot of ice on them, and when we took samples off of comets, we found a lot of rock in them. So these bodies, which some might be really, really big, are actually in long-term orbits and expand over about a light year, even maybe 2 light years in distance for the Oort cloud. So that's sort of our solar system as seen from above. Now, if I take and fly down here and look from the side, what I'll notice is that virtually all the planets' orbits are very close to being in one plane. They're inclined to some extent, 1 degree, 2 degree, that sort of thing. And Pluto's sort of the worst. I think it's like 13 degrees or something. You can look that up yourself. It's not that important. The main thing is to know that they all are mostly in the plane. And that's yet another reason to think of Pluto as different, because the one that's furthest out of the plane is Pluto. So it's really is that. Plus, remember, Pluto it's not a gas giant. In fact, it's smaller than our moon, and it's more like a big ball of ice. It's probably got a hardcore center that might have some metals in it, but it's mostly made up of ices and stuff like that. And in fact, instead of like volcanism and plate tectonics and stuff like that, everything is driven by the freezing and unfreezing and cryogeology, if you will. So Pluto is quite different. It does have, I think the last count was 4 moons. It might be 5. I can't remember. But the recent mission, the New Horizons missions, went there, got tons of beautiful photos. Definitely recommend you check those out. But as I said, when you fly down to the side of the solar system, you know that all the planets are basically in that same plane. So those are the properties that we want to take into account when we try to generate a hypothesis. And that's why we got the nebular hypothesis, or the condensation theory of the nebula hypothesis, is from these facts. Now, there's also some exceptions that make it kind of weird. So, for instance, one thing we know is Mercury is basically tidally locked to the sun, so it always keeps the same face facing the sun no matter what. That's pretty normal. We can explain that with just regular gravity, just like the moon is tidally locked with the Earth, so that we always see essentially the same face of the moon, even though we can see a little bit more than 180 degrees of it, because sometimes we're on this side of the Earth and get to see a little bit of this side of the moon, and other times we're on this side of the Earth and get to see a little bit of this edge of the moon. So because of that, we get to see a little bit more than 180, but it's the same slice that we see all the time. The things that are sort of exceptions is like Venus. Venus actually does revolve in a counterclockwise direction, like I said before, but it actually rotates in a clockwise direction, and very, very, very slowly, like so slowly that it makes one revolution around the sun faster than it makes one rotation about its axis. So literally, its year is shorter than its day. So that's kind of an anomaly, and we think that's a result of early on, maybe during the heavy bombardment period, when things were flying every which way, and the what would become our solar system was just packed with huge chunks of rock and stuff flying every which way. Things maybe even on the order of the size of Mars, which is about half our radius, that sort of thing, were flying around. We suspect that Venus was in fact struck by something like that made it spin backwards. That's why it's spinning so slowly, because when you have a collision like that, it's going to have to take way more energy to completely turn it around and make it spin fast, and that much more energy probably would have resulted in it not existing anymore. We also think, for instance, our Earth was hit by an object maybe the size of Mars, and that slung off its outer materials, put it in a sort of ring type orbit around our Earth, and that slowly accreted itself into what's now the moon. and it was very close to us initially, so that's kind of neat. The other big anomaly is Uranus. Uranus is it's not rotating counterclockwise. In fact, it looks like it's been knocked over because the rotation axis, which you normally think of, here's the plane of the orbit, and you think the rotation axis is somewhere like this, like ours is tilted 23.5 degrees, and a lot of them are tilted, as you can see, like Saturn there, and so on and so forth. But Uranus is tilted, I think they even listed as technically higher than 90 degrees. So Uranus is sort of rotating like this as it orbits. So like one pole is always pointing this particular direction, or the axis of rotation is always pointing this particular direction. So when it's on this side of the sun, for instance, the North Pole or the South Pole, whichever one you want to call it, is going to have 24 hours of daylight. And then when you get over here, the North Pole is going to have exactly half a day of daylight. So weird stuff like that. We also, like I said, we do need to try to come up with some explanation for the asteroid belt and the Kuiper belt. We already got basically the Oort cloud. So that's the things we're going to take into account. But what we also need to know is what is the material that was available for us to form a sun, or for the universe, if you will, to form a sun and to form planets. So that's what our next slide is about. So if you actually use the spectrometer and actually look at the spectra of the moon, I mean, excuse me, I keep saying the moon, of the sun, you will get basically little dark lines. It's an absorption spectra, so you'll get little dark lines. Each set of those represents some compound or some element, and the intensity of those dark lines tells us roughly what percentage of the atmosphere of the sun is that particular element or compound. This is a plot of the abundance in atoms of all the chemicals and elements that we actually see in our sun. And in fact, it's mostly elemental, as you can see here. I don't think, matter of fact, I don't think I remember even seeing any compounds. No, I didn't. Okay, or at least, yes, yeah, I don't. But you can see really the majority of stuff by and large is hydrogen and helium. Okay, and this is also like a logarithmic scale. You can see because it goes 10 to the -2, 10 to the -1, 10 to the 0, 10 to the 1, 10 to the 2. So this is a logarithmic scale. But hydrogen and helium are by far the most prevalent. Then there's oxygen, and then carbon, and then nitrogen. And then it looks like silicon, magnesium, and iron, and neon, and then sulfur, and then aluminum, and cadmium, nickel, sodium, argon, krypton, phosphorus, potassium, titanium, manganese. Manganese is actually higher than potassium and titanium. So you can see these elements are growing less and less prevalent, but there's a ton of them. In fact, 70 of the elements on the periodic table are found in our sun's atmosphere, in its chromosphere and its corona, and even the photosphere. So that's, in some sense, the elements that the universe had to work with when it was creating our solar system. If it had other things than that, we would still see them in the sun. And in fact, the models that best explain how our sun behaves show us that stars about the mass of the sun, within a factor of 2, or I think maybe up to 4, and down to maybe a half the size of our sun, they don't have any circulation mechanism between the core, where all the fusions are occurring, and the outer parts, the radiative zone, the convective zone, and then the photosphere. There's no kind of circulation method that brings elements that are now created in the core from fusion out to the other parts. So we do suspect this spectra of the sun's atmosphere is an accurate representation of the elements, and possibly putting them together at the temperatures that you expect them to come together, you can see what elements we'd expect to see, and even rocks and minerals and stuff like that. Obviously, you're not going to have too many elements bonding with other elements to make molecules in the surface of the sun when it's 6,000 Kelvin. 6,000 Kelvin, 5,830 Kelvin, whatever it is. That's hot enough to make the energies between atoms that are bonded break apart. So the energy is too high. The oscillation energy due to the temperature is too high for them to form actual bonds. So you then have to go back and use chemistry and your knowledge of how these elements interact with one another at various temperatures. And
Excuse
then
me?
from that, you can say, okay, well, all these elements were there, but oxygen is probably going to combine with hydrogen to make water. Oxygen is going to combine with hydrogen and nitrogen, or actually nitrogen and hydrogen will combine to make ammonia. Carbon is going to mix with oxygen to make carbon dioxide and carbon monoxide, all that sort of stuff. Then you can start saying, well, what about the aluminums and the irons? And we'll find feldspars and things like that
Okay.
can actually come out of this. So that's really why we're going. And it's mainly the fact that there's no circulation that makes this an accurate representation of our nebular cloud. Does anybody have a question?
Yes, I actually have two. One a statement, and
Go
well,
for it.
basically they're both statements. I think I saw this on the last test. Excuse.
No
I'm
problem.
sorry. Excuse me. And I'm also pretty damn terrified right now. I actually have to ask the class this. Is anybody living near the military base right now? Because I'm hearing explosions.
Holy crap.
Like when you say a
Training.
military base, what military base?
I don't know exactly which one. All I
Are
know
you-
is that we
are you
live
in
Where,
Virginia?
where do you
Are
live?
you?
Where do you live? Because I know
Ocean.
the military base is near here. So where do you
Ocean
live?
Lakes, yeah, near the Ocean Lakes High
Oh,
School.
You're talking
Oceana.
about Oceana?
No,
That's
Yeah.
Oceana.
No, Dam Neck.
Yeah, Dam
Oh,
Neck
okay,
Road,
okay,
Dam Neck
okay.
Road,
Yeah,
yeah.
that's Oceana base.
Yeah,
They're
it-
doing
Actually, no,
exercises. They're
that's too
They
doing
do practice
um,
exercises there, yeah.
They were
They
yeah,
are.
because
They're doing,
my
um,
house
yesterday.
my house is just vibrating and I'm so scared right now.
You're good.
they're
wait, are
doing
you Matthew, are you paranoid?
Yeah. Yeah.
This
Hey,
isn't
Matthew.
Diagnosed Fellow Students Day. Let's go ahead and get back to where we're going. What was your question about astronomy? I'm glad you're safe, by the way. And yes, I even feel them over here from Harvey Point on the other side of Edenton, or actually on the other side of Hertford. And I'm out in Moyock, and I used to feel it in Grandy. So yeah, that's very typical for practice. So Matthew, what's your question astronomy related?
I think I saw this question on the last test.
And what was it?
I can't remember exactly what it was, but it had something to do with
The explosions
Maybe it-
triggered his mind.
Yeah.
Explosion? Like an explosion when the sun was created, you mean?
Oh no! Like no, I was talking about like the Oceana base explosions. I think they're doing something with C4 over there for training, or
Yeah, but I'm asking back the astronomy related stuff.
Oh yeah, this question right here. I can't remember exactly what it was, but I know I saw something like this on the test.
Okay.
I'm not sure if it had anything to do.
I'm sitting
with,
here on pins and needles.
Yeah, I think it had something to do with the light spectrum. I might be mistaken. It might not. It's in the same format, but it might not be.
Was it like
This
a little
particular-
spectrum of atoms or with orbits and little arrows pointing down and stuff like that?
Yes.
I'll get to that at the end of this presentation. Yeah, that I did discuss that, but I do need to discuss it with you guys again, so I'll put that at the end. Okay.
Okay.
All right.
Thank you, sir.
This actually doesn't take the whole class, anyways. Just intro to the formation of a solar system.
And sorry if you heard my little devil dog over there barking.
No
She
problem.
thinks she's bigger than she's
You can
actually
mute
is.
it if
It's
the
just-
dog barks.
yeah.
Anyway, so if you
Little
take
chihuahua.
that chart that we just made and then plot it on a table to make a little bit more sense of it, sometimes it looks a little easier, but this number might shock you. Hydrogen at 92.1% and helium at 7.8%. You're probably used to hearing it being more like 75-25, like this. Well, the difference is this is the percent in number of atoms and this is the percent by mass. And remember, helium is like 4 times as massive as hydrogen. So if you multiply 7 or 8 times 4, you get closer to 32, and that makes a little bit more sense. But that's the difference. This is the mass percentage, and this is the number of atoms percentage. But the main thing I want you to notice is hydrogen and helium, by and large, are the most prevalent thing, and then oxygen, carbon, and nitrogen. Maybe some neon, but neon, of course, is a noble gas, so it's not going to mix with anything. Those are the most prevalent things in the what would be in the nebular cloud if we're going to go on the hypothesis that our star was created in a nebula. And I'll show you nebulas and why we think that in a second. So the big thing to remember is, okay, well, if that's the case, then we're going to expect the most prevalent material to be hydrogen, helium, and then, of course, various mixtures of oxygen with hydrogen. Helium's a noble gas too, so probably not that, but oxygen with carbon, oxygen with nitrogen, hydrogen with carbon, nitrogen with carbon, so on and so forth, all those little things. All right. And that's going to come in handy in a second. So it turns out if you look at the evaporation point, or the point at which something comes from a gaseous state and goes to a solid or a liquid state, it turns out that happens at very high temperatures for some things, like what we call refractory materials are usually hard things, rocks and metals and minerals that only come together, or it takes a huge temperature to actually turn into a gas. So if you actually make a plot of the temperature versus distance from the sun, you see it goes sort of like this, right? And when you look at a certain distance away from the sun, you find that at that temperature that the sun has, aluminum and titanium oxides and metallic tungsten and osmium, all that kind of stuff. You can tell they put this gray box here, so it's covering up some of the key words. But that would have been the stuff that was able to condense out closest to the sun. And why that matters is when atoms, molecules, anything are in a gaseous state, they're too energetic for gravity to cause them to pull together. Gravity is a very weak force. Remember that universal gravitational constant is 0.0000000000667. So it's literally 10 zeros followed by a 667 is being multiplied by it. So that force is really weak. Whereas at high temperatures, the atoms and molecules are moving very rapidly, especially the lighter ones. So it's really hard to attract them to one another to make compounds and stuff like that. But we still have some at very high temperatures, and around 1800 Kelvin, we get aluminum and, like I said, titanium oxides, metallic tungsten, and osmium. Around 1600s, we get iron, nickel, cobalt, and their alloys. So iron, nickel alloys, iron alloys, nickel alloys, that sort of stuff. And then a little bit lower, around 1500 Kelvin, we get magnesium silicates. So various silicates, which basically means they have SO, I think it's SO2 technically, on the end of it. And notice all those things happen before we get to the orbit of Mercury. So that means those three particular refractory materials and other materials should be found, because they can actually turn to a liquid state closer than Mercury is. So all of those things, which was not a lot of what the solar system was made of, but it was prevalent. So it was there, present. So that would actually congeal or accrete into gravitational blobs that would pull them together and make little, rocks that became planetesimals that got bigger and bigger and bigger with other planetesimals, and then became protoplanets, which is on the order of tens of kilometers, whereas a planetesimal might be as big as almost a kilometer, something like that. So those were the early things. And not only that, that would also make you expect anything beyond the planet, it's condensing beyond the planet, is very likely not to be in that planet. So for instance, the 6 lowest temperatures for unionized iron or unoxidized iron is right here. And that's right about the 1 astronomical unit mark, a little bit outside maybe. That means we probably would not expect those elements to be in Venus. And guess what? Venus is in fact depleted of that. It doesn't have much of it, okay? So that's kind of interesting. But remember, the molecular cloud, the nebular cloud that our solar system was made out of, the thing other than hydrogen and helium that it had the most of were those ices, the things that would be gases but could actually turn to ices, like water ice, water vapor would be the gaseous form, ammonia ice. If it's really cold, you can even get carbon monoxide and carbon dioxide ice. And of course, carbon dioxide ice, everybody knows what that is, right?
Liquid nitrogen.
Carbon dioxide is what we call, dang it.
Dry ice, I think.
Yeah, dry ice. Yeah, it's ice that melts and basically sublimes, so it skips the liquid state and just goes to the gaseous state. But that's some of the stuff that's present. So what you see is one by one, as each of these come available, if they're closer to the sun where they come available than the planet is, then that planet will have a large amount of it in there.
You said
Okay.
dry ice, like you said carbon monoxide ice,
Carbon
you said,
dioxide.
or hydrogen?
Carbon dioxide ice is dry ice.
Carbon dioxide. Oh yeah, That's the fun ice right there. You throw it at people and it just
My bad,
explodes.
wrong one.
Yeah, I avoid recommending throwing hard objects at people, but other than that, yeah, I get you. I do a lot of demos with liquid nitrogen. That's pretty fun.
That would hurt.
Yeah, here's what I used to do. Okay, so long time ago, back up in Pennsylvania, we
In a
had
galaxy far, far away.
in our entire neighborhood had this gigantic cook-off, and sometimes we'd take a sledgehammer and smash this dry ice, and it would explode.
Yeah, yeah. We used to take it and put it in like a Pepsi bottle, like not glass but plastic, and that'll actually explode. But you got to be careful because the shrapnel really hurts you, even though it's plastic. So, all right. Well, so what we're seeing is another critical point happens right inside of the orbit of Jupiter, by the way. So just inside of the orbit of Jupiter, notice we got water ice, and water ice was 95%. Remember that previous slide? Or 0.95 condensed solid. So water ice is really, 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 really prevalent. And it actually condenses out around 273 Kelvin. Okay. So you can actually get it into a solid state around there, but even before that, it can at least get to a liquid state. But water ice, actually after that. So water ice is here inside the orbit of Jupiter. What that means is these planets from here on, they have access to all those refractory materials that precipitated or condensated out, like I said. So they can make rocky cores just like our sun did, or like our planets did, only in this case, that's going to happen first, just like with us, but it won't stop growing at that point because it then can get big enough where it can suck up the water ice. And notice how much room they got to work with. So, like I said, Mercury is 0.4, Venus is 0.7 astronomical units, Earth is 1, Mars is 1.5, and then about 3 times farther away than Mars is Jupiter at 5.2 astronomical units. So Jupiter basically gets to plow between, let's say, halfway between 1.5 and 5.2, and halfway between 5.2 and 9.5 astronomical units. That whole swath around its orbit is all the material it has access to. And because it's in that cold region that's less than 200K, it has access to all those ices. And then if it gets massive enough, it can even attract the gases, because the gases won't necessarily have to condense out. It'll just make like an atmosphere. And then, of course, you look at Saturn, and Saturn's got basically from 7.5 astronomical units all the way to about 15 astronomical units. So that big swath is all the material Saturn has access to. And then Uranus has access from about 15 to 25. And then Neptune has it from about 15 to 35. And then, of course, Pluto doesn't have that much, but it does got the Kuiper Belt stuff. So you can see these ices and these things that are so prevalent, other than hydrogen and helium, these ices, the ammonias and the carbons and the oxygens and the carbon dioxide and the carbon monoxide, methane, all those different things are the majority of what's left after you remove hydrogen and helium. And since that's the majority of what's left, they had a lot of material. So those planets became really, really large. Okay. Now, when the Nebular Hypothesis, in the Nebular Hypothesis, when you have the star actually finally ignite, we know that when a star first ignites, it's literally like a thermonuclear explosion. The star becomes a star. It goes from protostar to star at the instant that it starts efficiently fusing hydrogen into helium. And when that happens, it's sort of a chain reaction, because basically one hydrogen or 4 hydrogens forming one helium will not only form a helium, it'll also give off a lot of energy and neutrons and stuff like that that can actually cause other ones to have the same process, and each one of those can make other ones. So it's sort of a chain reaction, and it's a big explosion. And in fact, we expect the solar wind, at least in this first instance, to be about 100 million times more powerful than the solar wind is today. And that basically blows everything out of the solar system that's not bigger than a centimeter or 2 centimeters across. So that's the whole idea. That clears out, and that it puts an end basically to the planet building. So what does a nebula look like? So this is the Great Orion Nebula. If you guys have found Orion, and I'm sure you have by now, it's sort of, a lot of people mistake it for like a bow tie because it's sort of narrow. It's got 3 little stars that are a little off axis, and then it's got 2 stars down here, Rigel, and the back foot, and then up here I got Betelgeuse as the back shoulder, and then another star in front. If you look right along that belt and just below it, there's some little dim stars that look sort of like a scabbards to hold the sword. Right in there is where you'll find the Great Orion Nebula, and there's actually like two big major parts to look at there, and you can see it pretty well even with just binoculars. So don't be too afraid to go out and look at it even with your iPhone or cheap binoculars. But for instance, the new iPhone can even take up to, I think I got it up to 10-second exposures. So if you can hold it well, or my wife even bought me a tripod for my phone. If you can put it on a tripod and sit at 10 seconds, you might actually be able to see a little bit more detail of the Orion Nebula, even with your phone. The problem is, of course, as we learned, the aperture is quite small on a phone. So that would mean the resolution is going to be pretty bad. Even though I've got 3 of them, I don't think it's doing any interferometry, but it obviously is doing some kind of interferometry because this now allows you to take 3D photos. So that's kind of neat. So this is a beautiful one. And what I want you to understand about this is those absorption and emission spectra we've been talking about. If I looked in this region of the sky right here, notice there seems to be a star in the nearby background right there. If I looked at that, I would get a spectra that's both absorption and emission spectra. The absorption spectra would come mostly from the star. Okay, so the star is sending out basically black body radiation, like the curve that Planck explained, and then that light is going through a lower density, cooler gas. And as you can tell, it's probably a lot of hydrogen there because all this red right here is indicative of the hydrogen spectra. But the lines of the elements and compounds that are actually in this gas will be missing from that spectra. So you'll have a rainbow with little black lines. That's why they call it a black line spectra. That's an absorption spectra. But it also has a little bit of emission spectra, but the emission spectra, you couldn't be able to see it very well just because it's overwhelmed by the absorption spectra. But if you move just a little bit over and look without that star in the background, say right here, then you'll get nothing but an emission spectra. And that's what, nebulas put off, because all these stars around it, notice they're really, really bright and blue. Okay. Brightness and blueness comes from hotness, and hotness and blueness comes from big mass. And big mass stars, high mass stars, tend to live very short lives. And the fact that you're seeing so many short-lived stars tells you that these stars were created fairly recently. And that's why we think nebular clouds like this, there's other words for it, for the interstellar medium, molecular clouds and stuff like that. These should be putting off emission spectra while they're generating stars, because these new stars are radiating. All these stars around here are putting out a buttload of radiation. They're hitting the gas, causing the little electrons to jump up every layer it can, right? Every orbit it can jump up to, it will. And then we're looking at the gas as those electrons trickle down slowly but surely, because they don't like being in those excited states. Each time they go down, they send out a little burst of photons whose frequency represents the color that they appear. And if you multiply that frequency times Planck's constant, you'll get an energy difference between, say, orbital 3 and orbital 2, or orbital 2 and orbital 1. So all of this stuff would be an emission spectra, and this would be an absorption spectra. Again, this would probably be an absorption spectra, but over here you get an emission spectra as well. And you can see the different colors are really those photons of light that are escaping. And even just seeing that reddish color, I knew there was some hydrogen present. And better astronomers can look and see like this blue, and they'll say, oh, well, this blue's probably titanium oxide and maybe a little bit of helium, stuff like that. They're really good at that. I'm not that guy though. Okay, I'm not a researching astronomer or astrophysicist. Here's another cool one. This is the Rosette Nebula in Monoceros. Monoceros is actually very close to Orion, by the way. It's sort of the winter circle goes like, it's actually more like a winter football. Great excess undermines various industries, Marxism. No, that's the electromagnetic spectrum. No, 7 ridiculous astronomers cold peering at planets for Sirius, Rigel, Aldebaran, Capella, Castor, Pollux, and Procyon. Those brightest stars help you find 6 different constellations, and then smack right in the middle of it is this constellation Monoceros that basically looks like a line with a right angle and then a diagonal going across it. That's Monoceros. And in Monoceros, you'll find this Rosette Nebula, Rosette. This one you can see it's a lot of red there, so there's definitely a lot of hydrogen. This is another place. This is like a nursery for stars. This is where stars are being formed. The cool thing about Orion is virtually that whole constellation is made up of stars, the brightest ones anyways, all from the same nebular cloud. So though they may be, light years apart from one another, they're way closer to one another than they are to us. So when we compare stars that were all created in that same nebula, they're essentially the same distance away from us. So if one looks brighter than the other, that means the brighter one is actually more luminous. So you're comparing, because they're all roughly the same distance, you're comparing luminosity to luminosity instead of having to worry about converting from brightness to luminosity. So again, these are the kind of things that would give you emission spectra, all these pretty clouds around here. Here's another one. This one's really famous. You normally see just pictures of that part blown up, but this is a giant nebula called the Eagle Nebula. And I definitely recommend you look at as many of these photos of these nebulas as you can from Hubble. Hubble's got some of them where it blows this up. And imagine this, that little tower you see of gas and dust, that thing's on the order of a light year tall. So you're seeing something ginormous and it looks teeny in the telescope. I mean, if we looked at these in the telescope, we might be able to sense a little bit of bluish, maybe even a little bit of reddish on occasion, but generally we can't see any colors in them. But what we see is a blurriness. And in fact, that's why they're called nebula. Whenever astronomers with older telescopes would look and they saw a blurry area, the Latin word for cloud-like is nebulous. So that became our nebula. So anything blurry now is a nebula. And a lot of those nebulas are places where stars are born, but some of them aren't. Some of them are planetary nebulas, for instance, and they were called planetary because they often are circular and therefore look like a planet, but in fact, they're the death shroud, if you will, of an exploded star that died. So when the star dies, it blows off all of its material, and then that moves out bigger and bigger. And we're looking at it at one point in time, and we can see that the cloud's moving away and towards us using the Doppler effect. And so we know that it's actually propagating outward. But those nebulas, like I said, are not birthplace of stars. That being said, the death of a star can generate future star birth when the shock waves and things of that sort force bits of matter closer and closer together so that stars can form. So another thing I want you to see about this, these little globules that you see down here, those are like little areas where a new star system is forming. It's clouds of gas and dust, and it's got a little cocoon around it that actually helps the star grow because it actually acts as a blanket that doesn't let all the radiation out. So as the star is starting to form, it's actually generating energy from occasional nuclear fusion and stuff like that, and that radiates energy, and it gives off energy from, basically from matter falling in towards the center and so on and so forth. But the more that energy that gets away, the less it goes to getting the core hot enough, which is basically a 10 million Kelvin mark. But once you get to that 10 million Kelvin mark, then you can start fusing hydrogen and helium fairly efficiently. And these little blobs of gas and dust are actually acting as blankets to speed that process along. And they're also shrinking because they start off sort of, weird shaped or whatever, but there's always an average random rotation axis. So the rotation axis of this guy might in fact be like this. And that just comes from the average velocities of everything that's moving in all sorts of random directions. And that will ultimately be sort of the rotation axis. If this turns out to be a one star system, it'll be the rotation axis of that one star. And then the planets will flatten out in a plane perpendicular to that roughly. And it does so for the same reason that when you take a ball of pizza dough and you spin it and throw it up in the air, it widens and flattens. And that's what's going on according to conservation of momentum and the forces of gravity and the fact that the ones that are above and below the planes are constantly being attracted by gravity. And when they go through the plane, they get slowed down, they run into stuff. So eventually the plane will flatten out, flatten out, flatten out. When our solar nebula did that, it was actually about 10 billion kilometers across in diameter, in other words, which is basically a little bit bigger than the orbit of Pluto. which makes sense, right? You'd expect all the planets to come in there. The individual pieces, by the way, would break up, and the laws of physics suggest that they would all rotate counterclockwise if the whole cloud was spinning counterclockwise. And that starts to explain why we see the planets rotating as they do, why we see them all in a plane, why we see the big central masses or sun rotating in a counterclockwise direction, all that good stuff. Any questions about that? So here's another one. This is 30 Doradus. This is a photo from Hubble Space Telescope. At the end of the slideshow, I have all the links, citations, if you will, to the people that created these photos and the websites that I got them from. But this one is really cool because look at it's making a cluster of stars there, and star clusters are really cool. Imagine living in a planet orbiting one of these stars and having this many stars that close to you. It would be just awesome. And this is not unlike what I see when I look into the constellation of Cancer. Cancer is not that bright of a constellation. It is actually quite dim, and until you see it for the first time, you have a hard time finding it. But I can tell you, it's right in between Castor and Pollux, the two bright stars that are the sort of heads of the twins of Gemini, and then the backwards question mark or sickle that is the head of Leo, the lion. Right in between those two is a sort of triangle with a little triangle inside. But you don't see those triangles initially. What you'll see is a little blur between Castor and Pollux and the stars of Leo. You'll just see a little blur, especially out the side of your eye. When you look at that with binoculars or a telescope, would even be better, you'll see a bunch of stars like this. So again, that's a really cool thing to see. It's awesome. I highly recommend, even if you have an old cheap telescope that your mom gave you when you were 5, it's still infinitely better than your eyes. So go out there, look at the blurry spot between Leo and Gemini, and you will see something really pretty. Look below the belt of Orion, and you will see something really pretty. Okay. Here is a T-Tauri. It's actually the T-Tauri star. So this is the cloud, a gas cloud like we expect. It ultimately created our star system, our solar system. You can see there's something hot at the center that's growing, and that would be like the protostar just before it ignites. And we think it hasn't ignited yet because this whole big cloud's here. But notice it does appear to have sort of a disk to it. That would be the orbital plane that all the planets would form in. And these things are still orbiting this way and this way and that way and this way and all this stuff. But over time, and time is actually on the order of maybe 100 years. So it's really quick on geologic and astronomical time. 100 years, you might have most of this stuff completely disappeared. So it's pretty cool. Now the other planets going molten and all that stuff, that's going to take on the order of 10 million years. So that's a little different, but you can get the dissipation and flattening and on the order of 100 years or maybe 1,000 years, something like that. So that's another example of an actual star system forming. So this is the idea of the cloud of gas and dust that would be a nebula that makes our solar system. Okay. And like I said, when you take you are in the 131 class, we're going to learn about interstellar material. In other words, the material between the stars. And there's a lot of different classifications, molecular clouds and whatnot that we're going to go through. But basically, we're just going to say it's a cloud of gas and dust that's dense enough to where things are connecting each other gravitationally. And because statistics say that everything's going to have an average rotation, this average rotation is going to create a rotation axis. Everything's going to go this way. Notice that's counterclockwise, just like I said our planets do. And conservation of momentum, laws of physics, blah, blah, blah. All that stuff causes this disk to slowly flatten and widen. And basically the majority of the matter is going to exist, will exist in here, and will form what we originally called 9 planets. Also, the things in the asteroid belt and the things in the Kuiper belt that are now dwarf planets, they would have formed around the same time as well. So Ceres, C-E-R-E-S, which is in the asteroid belt and is bigger than our moon, that would have formed as well. All these things are just forming by gravity. And then, of course, they're getting molten because they're so big that they've basically put so much pressure on the materials inside that they've crossed the threshold from solid to liquid. And then that liquidness, that moltenness, if you will, allows them to form in little spheres. Now, when we model something like this with massive computers, like I talked about at the end of chapter 6, we can model these very robustly, and we see that those individual planets that would be part of this would ultimately rotate in a counterclockwise direction as well. So the laws of physics are telling us that this kind of cloud does this and results in all the objects orbiting counterclockwise and all the objects revolving counterclockwise. Revolving is actually the same thing, I should say. Rotating counterclockwise. Revolving and orbiting is the same word. And then rotation, of course, is counterclockwise. So that's kind of a neat thing. And that's why we believe the Nebular Hypothesis is the correct hypothesis as best we can tell. But we still call it a hypothesis because we find in some areas things like hot Jupiters. And if you see a hot Jupiter, that doesn't fit, right? Because a hot Jupiter means a really big thing, and a really big thing would have to have access to a lot of matter. And the thing that has access to a lot of matter would normally be very far away because it's got to get cold enough to have all the excess matter that's in the form of ices to attract to it. So if we find a Jupiter like in the orbit of Venus, that doesn't fit our nebular hypothesis, and we find those. We've actually found Jupiters close as Earth and stuff like that, things that are on the order of 9 or 16 or 10 Earth radii, but only out about the distance of the Earth. So those things make us think there might be other mechanisms. They've postulated that giants like that can migrate inward. They've postulated that maybe large giant gaseous clouds like that could actually migrate outwards, all sorts of stuff. So it's still not completely settled science. Okay. So these links on here are really great. So if you need any more explanations of this, I definitely recommend this one by Fraser Cain. That's really good. This one by NASA. This one by space.com. And then this site in general is just awesome. It's called Ask an Astronomer. It was created by the astronomy department at Cornell. Michelle Thaller does a lot of wonderful videos in there. And for instance, like when I asked you earlier about green stars and told you that you could write a short paper on that for AstroPoints, you can find a very good explanation of why we don't see green stars at this website. So I definitely recommend it. Here's where I got all the slides. Slide 2 came from here. Slide 3 came from this website. Ibid just means the one above it, and this means the one above it, so on and so forth. So basically, slide 3, 4, and 5 all came from the same source, the same website. Slide 6 came from, actually, the photographer was Francesco Battistella. I don't know, but it looks like Stella on the end. That's kind of cool. And as the elf buddy said, Francisco, that's fun to say. Slide 7, the Rosetta Nebula came from here. It was photographed by Gene Dean. The Eagle Nebula that I showed you was photographed by Jimmy Walker. The Doradus 30 Doradus was by NASA, ESA, F. Parseus in Italy, and R. O'Connell from University of Virginia at Charlottesville, and the Wide Field Camera 3 Science Oversight Committee. And then the T-TARI system was taken by C. and F. Rodier with the IFA in Hawaii, and CFHT as well, which people in the know what that is. And this is just me repeating the same slide because that's the way I do things when I make a slide. Anybody have any questions on that? So that's a really brief explanation of how we think our solar system formed. I've shown this topic or done this discussion before and had people confuse it with the Big Bang. This is entirely separate from the Big Bang. The Big Bang, which wasn't big and didn't bang, was in fact all of the universe, which includes the space itself, coming out of nothingness and then starts expanding. And initially it's completely black, and then at one instant it reaches a low enough temperature where the electrons can collect against the protons to form atoms and elements. And because of that, all of the light except for those absorption spectra can actually pass through. And that burst of light is in fact what we now see as the cosmic microwave background radiation. This is just a cloud of gas and dust, sort of doing the opposite. It's more like contracting, but it's expanding in one plane, and it created our solar system, specifically the inner and outer planets, the asteroid belt, and the Kuiper belt. And then, of course, the Oort cloud would just form over time from random things coming in near the large planets and being slung off in random directions. So anyone have any questions? Well, before you guys split, of course, we have till 11 o'clock. I wanted to address the question that Matthew had, because that is a very important question. And I want you guys to understand it. So
actually, we have until 10:45, remember?
Oh, yeah, 10:45. Thank you. Appreciate that. Yeah, 9:30 to 10:45. Excellent. Okay. So the question that I used to do is I used to just take, and I should probably show you my camera, showing my document cam since I'm writing on a document. So you say a nucleus here, and remember the nucleus of the atom is really, really small. Like if you blew it up to the size of a grapeseed, which is literally about that size, if not a little smaller, then the orbits of the electrons would be really, really far away, so much so that if you put this at the 50-yard line of my Washington football team's football field,
It'd be at the edge, wouldn't it?
Yeah, the orbit would be out beyond the parking lot. So it's really crazy. It's literally like a factor of 10,000 larger. So what we'll have here is a non-scale drawing, and this would be, say, the first orbital, and then the second orbital will be closer, and then the third orbital will be closer still, and then the fourth orbital will be closer still. So one thing, you can draw transitions like from here to here, here to here, here to here, and then let's say from here to here. Now, if I draw the arrows down, pointing downward, that means the electron went from a high energy state down to a low energy state. And conservation of energy says you don't just destroy that energy, so it must be shot out. That means it's an emission spectra. So that's one of the questions that can come from a diagram like this is, once you see the arrows pointing up or down, is that an emission spectra or is that an absorption spectra? I'm going to draw the arrows down. And everybody, of course, now knows that that is an emission spectra. So first answer. Emission. I know there's not supposed to be two M's there. I don't know what happened. Anyways, that's the emission spectra. Okay, that's also called the bright line spectra. And according to Kirchhoff, that is due to a low density, a low density gas that's been excited by something else. So like when we look at that nebula, without the star that's lighting it up behind it, we just see the cloud, and that cloud has been energized from radiation hitting it and caused all the electrons to jump up. We're now seeing them electrons that weren't comfortable up here falling down. And each time one falls down, it lets off a photon. So a little photon will shoot out. And the frequency of that photon is such that let's say this is E1, this is E2, this is E3, and this is E4. This is such that E3 minus E2 is equal to H times F. That's the frequency of that photon right there. Okay, and of course you can use frequency R wavelength because it's also HC over lambda. You can use frequency R wavelength to specify a particular color. So that's why we see the colors that we do. The photons that are emitted have a specific frequency or wavelength, and a specific frequency or wavelength has a specific color. So these are all emission spectra. If the arrows were drawn up, that would mean the electron was in a low energy state and then felt compelled to jump to a higher energy state. You can't just create matter and energy out of anything. So what happened was an electron happened to be, or excuse me, a photon happened to be flying by, and its frequency, when you multiply it by H, happened to be exactly the energy difference between E1 and E3, and it spontaneously disappeared, and the electron spontaneously appeared up here. Okay, that type of scenario, when the arrows go up, is an absorption spectra, also called a dark line spectra. Now let's get to the more serious questions. So I'm going to call this one 1, this one 2, this one 3, and this one 4. So the number is to the left of the actual arrow. I know you can't see those. I wrote them too small. 1, 2, 3, 4. Okay. So I might ask you, I would say the 4 photons are let's say one in the X-ray, an orange one, a microwave, and a blue one. Okay, those are the photons. So which transition created the orange one? That would be a question. So the way this works is, remember, the energy difference is equal to h times f. That gives the color. But the energy difference is also related to the length of these arrows. The longer the arrow, the larger the energy. So this one must be the highest energy, second highest, third highest, and then the lowest. So if we take our great, remember the mnemonic, I know this is going up on YouTube, so I want to remind everybody, I made up this mnemonic because Rush Limbaugh always picks on us teachers. I'm a big Rush Limbaugh fan who just recently passed away, but he always picks on us teachers saying we're all communists. So I like to do this just as sort of an homage to him also picking on him. Great excess undermines various industries' Marxism rules, and we know that this end is long wavelength and low frequency and low energy and low temperature, and this end is is short wavelength, high energy, high frequency, and high temperature. So that's what this side is. And of course, we also know that this breaks up into, as I've written this, it has to be VIBGYOR. Okay. So what we have are a photon from the X-ray, which would be right here. We have a photon from orange right here. We have a photon from microwave right here. And we have a photon that's blue right here. Okay. So those are our four photons. Now we just have to say, well, which one's the highest energy? Because that corresponds to number 3. So on this scale, which one's the highest energy?
X-ray.
X-ray. So this will be transition 3. The next highest energy, which is number 2, which is number 2, is blue, right? And the next highest energy, which is 1, is the orange, exactly. And then finally, the lowest energy is the microwave, and that must be transition number 4. So I gave you 4 different questions there, basically. I could ask you, which one did the microwave? Which one did the X-ray? Which one did the orange? Which one did the green? Or no, blue? Which one, and so on and so forth. Which one did the X-ray? So there's 4 different questions I can ask out of that, plus another one for whether it's an absorption spectra or an emission spectra. But I can also ask you to put those photons in order of increasing wavelength, or in order of decreasing wavelength, or in order of increasing energy, or decreasing energy, or increasing frequency, or decreasing frequency, or increasing temperature, or decreasing temperature. See how many questions I can make out of just this little construct? And if I draw another one and put the arrows pointing up, I got that same set of questions all over again. Okay, so these questions are very important. These are sort of our chance to test you on literally quantum mechanics, but without the math. So it's a good, like, university level question that doesn't require math. It requires, multiple steps to solve a problem. So there's another type of problem that I want you to make sure you know. Now, Matthew, did you understand that before I show you this other type of problem? Because I only got 2 minutes.
Okay, so what I don't understand is the order of the 1, 2, and 3. Oh my God, number M. No, letter M right there. That's 4, right?
Yes. The reason why that's so is, remember the links. The links are the energy, basically. A long length arrow is a high energy. A short length arrow is a low energy. So it all depends on you knowing your great excess undermines various industries' Marxism rules and knowing what order that represents.
But why does the line number 4 reflect M?
Because line number 4 is the shortest.
Uh-huh.
It's very short. That means it's the lowest energy. So I find whichever photon was closer to this end, because this goes, like I said, from high energy to low energy. So the first one I come to from this side is the microwave. Therefore, it has to be 4.
Is it always that orbit right there that's going to reflect M, or can it be others?
It can be others. For instance, if I did all of them are radio waves, except for one of them, which was a microwave, then if they're all radio waves and one of them's a microwave, then the microwave would actually, in that case, be this long one.
Okay.
Because remember, it's just you draw an arrow on the spectrum to represent each of the photons I give you. And then you go back and say, all right, the lowest energy will be the shortest arrow. Which one do I hit first? Well, I hit microwave, so that must be 4. The next one I hit is orange. Well, that must be 1. The next one I hit is blue. That must be 2. And the next one I hit is 3. That must be, or the next one I hit is X-ray. That must be 3.
On future tests, will we have to draw the arrows ourselves, or will they already be up there?
No, they'll already be there, and I will ask you what them. I mean, there is a problem I could make and say, this is an emission spectra. Draw the arrows on it, but I usually don't do that.
Is there any way to find the arrows? Like, if you were to give us a question like, which place would X-rays reflect? Is there a process in order to find these arrows before we answer the next question, like an equation or something?
No, I mean, the equation for the length of these arrows is just this. But I don't make you do any of that. So, and there's ways to calculate that stuff, but I would never give you that because that's more mathematical. Now, I am getting ready to cover another thing to make sure you guys know, but the time is actually up, so you are actually free to go. But if you have any questions, please stay, and I'm going to show you this part in a second. Have a good one, Amy.
I'm going to stay. I want to see what this is.
Okay, so this is the Planck curve that we talked about when we first started talking about quantum mechanics. This is the one that Planck did a crazy thing and figured out that he had to use E equals HF times the integer to understand this curve. And what I'm saying is this curve is here and the visible spectrum's here, you should be able to tell me what color the star will appear. And what the rule is generally this represents the color of the star. The wavelength at the peak, if you figure out what color that is, that's supposed to be the color of the star. But in this case, the wavelength of the peak is outside of the visible spectrum. So what does it do? Well, it looks like the one that has the highest energy, which is that right there. Notice that's on the violet side. So I call that violet, indigo, or just plain blue. Everybody just says blue, by the way. Now, if you had another one like this, say, okay, now this time the peak's right in there and it looks like the peak is at green. So this star would be a green star. Oddly enough, I chose green. Okay. And if you had a star like this and it had its curve like this,
that'd be outside the visible spectrum, wouldn't it?
Yeah, this one's again outside the visible spectrum, but we look where the Planck curve actually hits the visible spectrum. So this star would appear red.
Red. Okay. Yeah, I see it. I see it now. That actually does make a lot more sense than what I thought before, because I thought before that the peak is always the one that's going to be seen. But no, it's not. It's like looking through a magnifying glass. You ignore everything else, but most important thing is in this color spectrum here.
Yeah, what is the highest point on this curve that's within the visible spectrum?
Is it in that visible spectrum because like the light's being diffracted through gas?
No, it's basically Wien's law, which says the temperature is equal to 2.9 times 10 to the 6 nanometers Kelvin over wavelength in nanometers. So basically the star's temperature here is a low wavelength. So its peak is going to be way out here. This is the actual equation for the peak wavelength. That's Bean's law.
Yeah. You can't really see the star at its peak because it's outside the visible spectrum.
Right. And peak is where it has to be because the laws of physics say it's going to be at 2.9 times 10 to the 6 nanometers per Kelvin divided by the wavelength. So, or divided by the temperature in this case. So whatever the temperature of the star is, that's going to dictate where this peak is. If you did the math, you could actually figure out what that wavelength is. Same thing with this one. The peak is where the temperature makes it be. And the same thing with this one. The peak is where the temperature makes it be. So go ahead.
So whether you could see the peak or not is basically dependent on biology. Humans can't really see the peak of something outside the spectrum, but
right. We have
other animals can.
Yeah, yeah. Snakes, pit vipers can. Pit vipers can see outside the visible spectrum a little bit. Yeah. I answered a couple of questions for you. Does anybody, Jamie or Amanda, do y'all have any questions?
We'll
take turns.
I have a question, but I have to ask you like by myself.
Okay, no problem. Matthew, did you get that?
Oh yeah, I did get that. Please please make sure to what I asked you at the beginning of the class.
Oh yeah.
Yeah. Thank you, sir. Have a very, very nice day.
All right, you too. Have a good one.
Thank you for clearing everything up for me. Yeah,
No
test 2 and the accommodations test 2. I wasn't sure if I was allowed to take the accommodations test because like it said.
I'm trying to get rid of the accommodations test. You could have, it wouldn't have mattered, but I figured out a way that I can do it without making a special accommodation test. So have a good one, Matthew.
Oh, and also the constellations tests. Yeah, I like my paranoia, you know.
I remember. Yeah.
Thank you so much, sir.
No problem. How about you, Jamie? You got a question?
Very nice day, everyone.
I saw you logging in and out several times. I guess your internet connection wasn't that good.
Oh yeah. That's another thing. I'm in California right now.
Oh, cool.
So yeah, I had to come back here. But so I sent you an email about some family stuff that was going on.
Let me turn this off. Hold on.